As this is getting started up, probably half of the talks today mentioned chemical stressors, chemical inputs, but no one really went beyond that except Carolyn a little bit, thank you, and George. So I'm going to kind of be swimming beneath the surface here a little bit and try to relay some of our experiences, lessons learned, and I think some of the really promising directions that are coming along with our ToxCast, Tox 21 program, and new developments that Carol mentioned. Very simple schematic here to sort of lay out the underwater landscape a little bit. Test sample has a lot of considerations, actually. I am a theoretical chemist, but in the past few years, I've become a chemical manager of actual test samples. I've learned a lot. Almost everything we've talked about are dealing at this generic substance level where we're aggregating, integrating data from public sources. It's all generic. It doesn't become useful from a chemistry standpoint until it becomes linked to chemical structures. And that's a crucial connection, integration that has to be made. And for prediction, it doesn't become useful until those structures are converted to other representations that can be generalized from the structure we know something about to the structure we don't know something about. So these four layers are really where I am going to be trying to visit and comment on. And this increasing level of aggregation that helps to push us into this plane where we can begin to talk about predictions. The test sample is where you make that linkage between an experimental result. If that test sample and the generic substance are not correctly linked, you do not have a correct linkage between your experimental result, you introduce a certain percentage error. If that generic substance chemical name does not match that CAS, and they actually represent two different substances, I estimate 2 to 15% error rate in the public tox literature based on our 10 years experience now curating. Then you fold that error rate into your aggregation of toxicity data as you move toward modeling. The structure assignment to the chemical name and the CAS, keeping in mind that CAS, I don't know how many people are familiar with this, CAS is our entry into the historical public tox literature. It is owned. You pay to find the definitive CAS record telling you exactly what structure should be assigned to that CAS. We typically use STN for about 5 to 10% of our verifications because the public resources are not definitive enough to do that. You cannot go to PubChem and get a definitive CAS name assignment. And then finally, the top level is where we begin to construct the ability to generate chemical groupings that give us this ability to generalize about the chemistry in relation to the toxicity. Matt showed the schematic already, just laying out the landscape of our ToxCast and Tox 21 efforts. The point I want to make about this is you see this corner here is our overlapping region of ToxCast with Tox 21. We constructed this library to overlap many different inventories. So data integration was central to this. This chemical library underlies everything we're doing. It is our probe set. It is what we are using as our tool to construct an intermediate layer of biology to better understand toxicology. So it's underlying everything. So issues of curation, data quality, if we don't do as good a job as possible at this level, we carry and imbue the next level with an error rate that becomes unacceptable, in my view. So one of the big, hearing all about the importance of public distribution of data, EPA, I think one big advantage of government research is we don't necessarily have the pressures for public funding, for grants that other agencies do. What we don't have typically is a lot of personnel and a lot of money to do things. So what we try to do is we push data out. We push it out in ways that we can leverage our data to get other people interested in using it. And that's what we've tried to do within our group, is push everything out into the public domain. So in this case, I mentioned generic chemicals, Actor, ToxRFDB, DSS Tox are all dealing with this space of generic chemicals, linking it to data. ToxCast and Tox21, however, are dealing with actual test samples. We procure these samples from suppliers, we solubilize them, we plate them, we send them to assay providers, we make that linkage, then we work our way up the ladder. And then finally, Actor is this gross Uber data integration where we're just trying to pull all these data together. Now, Actor, because of the nature of the public data, it's aggregating based on CAS, not structure, although it's trying to bring in structure, but the big structure databases out there are things like PubChem. PubChem is, if you're all familiar with PubChem, it's a user-depositor system. With a user-depositor system like Geo, RayExpress, PubChem, you get wildly varying quality in what goes into those resources, but it's still very useful. So as we constructed our ToxCast Tox21 library, think in terms of, we basically initially just went out and said, what are all the chemical space that we should be interested from an environmental health standpoint to try to deal with this problem of predicting toxicity. So we went to many different lists of chemicals, aggregating by CAS through Actor. And what you begin to see, actually, you go to all these different silos, once you mash them together, you're getting lots and lots of overlaps. So these pesticides may also be fungicides, maybe agrochemicals, maybe drugs. You're getting lots of overlaps. And we actually designed this library to some extent to maximize those overlaps. Every time we get an overlap in different spaces, we have the potential for different pieces of data to pull together, data integration, as well as a bigger bang for our buck for one chemical that's of interest in multiple venues. So we actually have a lot of overlaps also with in vivo data sources, which was also by design. We built a sample registry to track at a very detailed level each one of these chemical samples, again, to try to get it right at the bottom, work our way up. We can always genericize later on, but we have that underneath layer. Unique to this effort, pharma typically does not do analytical chemistry when they're screening for drugs. It's kind of a quick and dirty, let's hone in on the active space. We are doing analytical chemistry underlying ToxCast and Tox21 to try to actually bring that additional data to understand when we're not getting the types of effects that we expect and what might be affecting the modeling. Why this is so important, and I'll touch on this again later, is because the battle with structure activity, with prediction in this area, it's always about numbers. We never have enough statistical significance. It's the signal noise problem, always, we're battling with. And if we can get the noise down a little bit, we have a much greater potential to see our signal. So we actually procured for the EPA portion of Tox21 over 4,000 samples. The chemical data quality issues, I'm not going to go into this, I could spend all day, but above, in the generic space, as I said, 2 to 15% error rates in association of CAS with name, incorrect structures, all sorts of errors that we see typically in the literature, in EPA databases and NTP databases. I recently had the experience of helping to clean up a collection of hydrofracking chemical databases. To give you an idea, we started with about 1,600. The final data set is 1,100. What happened to those 500? They were duplicates, misspellings, invalid CAS. That's just one example. Beneath the iceberg of our test samples, you have samples that you bought that the supplier said was this. It's not quite that. It's a salt form. Maybe it's a totally different chemical. Suppliers have different levels of reliability. We have samples that disappeared from the bottle. They must have been volatile, but they're certainly not going to get into the test system. We have samples, probably 5% of our phase 1 300 chemical library decomposed due to hydrolysis, which upon further digging we understood was because they were a salt and they were, so there's chemistry under the surface that can help us understand why we're getting the results we are, and we ignore it to our peril. The DSS Tox project, I started many years ago coming into this field as a theoretical chemist trying to do SAR. There's never enough data. There's never data to do what you want to do. So I put my energies in just creating this resource, pushing curated data sets out to the public domain, because my feeling was you've got 10 people modeling the cancer potency database. Each one of them has to go pull down PDFs, annotate it. They all do it wrong. They all do it in different ways. Let's just do it once, and everybody's working off a common data set. So we pushed out about 15 of these data sets. They span about 17,000 compounds, which is a drop in the bucket with respect to the large chemical universe. But it's beginning to provide substantive coverage of toxicity exposure space. When I say standards here, I'm talking about just try to get the association of the Cas and name correct. Try to get the structure association with the Cas and name correct. That's what I mean by standards. So we put a lot of effort into that piece of this. Now, when we publish these files, they're in a format that a chemistry modeler can use, a structured data file. And this was actually very helpful to the chemistry, cheminformatics community. It is a public standard. So every commercial, every application can import and export SD files. Well, no toxicologist has this on their desktop. There's no place you could go on the internet to actually read these files and put them out. So we made this little browser with public tools to allow people to access the files that we created on the internet to do these simple searches. My other objective here was to try to get the biological community comfortable with the notion of structure searching. I would guess that a very small percentage of people go to ChemID and PubChem and actually do a structure search. Most of them do a Cas and a name search. The structure search in here just comes out very easily, and you can actually export the SD file, and you can get a quick sense of analogs. And my hope was that a light bulb would go off, and people would say, oh, well, that's actually pretty interesting. Now I can actually see multiple chemicals that look similar, and I can start digging deeper and think about my problem more in a structure space instead of name and Cas space. Once you get structures, you can begin to do all sorts of things. And this is just an example with our ToxCast library, phase 1, phase 2. I've projected onto a property space computed from the structures, just to give you a visual sense of how much we're covering this chemical space, knowing that this is our probe set. We want to cover enough chemical space that we're really hitting a lot of relevant biology to mapping out our toxicity mechanisms. Pharma, in this case, we have donated pharma, failed drugs with toxicity endpoints that we're projecting onto the space. E1K are chemicals chosen for endocrine disruption screening program testing. And then Tox21 is a much larger set of chemicals. And the point here is simply that we can begin to look at the scope of our chemical space as our probe set. We can also pick out 2 points that are near each other in this property space, and that can give us a sense of where we might want to look for similar biology. Another way to do this, and I'm going to pick up on this point, and again, this is in lead scope, is looking at a projection of different components of our Tox21 library onto a set of features. And you can see that each one of these chemical libraries, about 3,000 chemicals each, are hitting different functional categories differently. But because we're looking across with a common vocabulary, with a common set of chemistry goggles, if you will, we're able to compare these different libraries. They may be totally different chemicals. And we can begin to see where we're getting feature enrichment by adding chemicals that may be drugs versus pesticides. And we're also getting areas where we're filling in some features that are not present in some of the environmental data sets. And the reason that's important is because we're looking also for data that's attached to these chemicals. So data that's attached to chemicals, attached to features, are then brought into the larger predictive sphere. We can do the same thing with chemical reactivity. I'm trying to actually, the big point of my presentation today is to get you to think in terms of another type of vocabulary for chemistry, and that's what we know about chemistry. And that's, to my mind, what's very much been missing in the way that we try to model toxicity. We know a lot about chemistry, but it's not effectively translated into the prediction sphere, in my view. So why is the chemistry needed? There was a paper published this year, actually, that looked at our original phase 1 data that was primarily pesticides, where we had 500 assay results for 300 chemicals, lots of data. They did some very sophisticated machine learning, statistical approaches, many approaches, and just tried to predict in vivo toxicity endpoints, ones and zeros, with our HTS 500 assays and our 300 chemicals. 300, 500, with no structure to this problem, which I think probably everyone in this room can predict that this would fail, which it did. And I believe the reason it fails is we've got a very noisy data set. We've got lack of statistical power. We don't have the data to do it in this way. The reason our group has had, I believe, some significant successes, even in modeling phase 1, is because we're structuring the biology. We're not just looking at 500 assays. We're mapping those to gene targets. We're trying to organize them in terms of pathways, and that's when you begin to see the patterns of in vivo to in vitro data. But it's like one eye is closed. In the first case, both eyes were closed and one arm around its back, and and the chemistry is still blank over here. We need to do exactly the same thing. We need to distill the chemistry instead of, I can pull off the shelf 6 different programs and compute 10,000 chemical descriptors. That's not going to help us solve this problem. We need to pull that medicinal chemistry, pharmacological knowledge, distill it in the same way we do for the biology and distilling, an assay to a gene target to a pathway. And that's what's going to help us deal with the numbers problem, in my view. And so here's, well, my little fine didn't work right, but this is just a snapshot down in the weeds. The devil's always in the details, and I've been living in these details for a while. But you go up to the generic substances, then you actually have to process these structures. You've got salts, complexes. You distill those into parents, but maybe there's some differences there. Maybe you can't do that all the time. You need to ask, is it appropriate to do that? You need to actually look at the data and see if it matters. So you get desalted compounds. Then I'm going to argue one way to approach this problem is to further distill and map these very varied structures onto a smaller vocabulary. And what that helps you to do, it helps you to, as I showed with the lead scope slide, it helps you to begin to compare across. It helps you to begin to populate, here's a known chemistry space that has coherent function. Let's populate that with in vitro data. Let's just map all of our assay results into that area of chemical space. And if we agree to start with maybe this vocabulary, so what has really changed in this field? This is a big view of our big problem right now with ToxCast and Tox21. We have 3 very big data domains. In vivo data becomes, if we want to model at the level that's meaningful, we don't model developmental toxicity. We model cleft palate in rats. We get that species resolution, we get that endpoint resolution, but then we lose all our numbers. So the data curation that ToxRefDB and other efforts is essential to build up those numbers. Then we generate all this in vitro data with all these bioprofiles of hundreds of assays, and we can better than hope to build a biological argument to model fewer data. And then we bring in the chemistry. So at each one of these planes, we have to aggregate, and we have to bring a knowledge, prior knowledge to help us to structure. And so our approach and the way we're trying to do this is to say, not just blindly compute properties from structures, but try to incorporate and feed knowledge into some hypotheses. And there's no one right way to do this. We could have multiple feature sets, multiple ways to incorporate. And where do we go to find this knowledge? We can look to some of the existing predictive alert libraries. We can go to chemotype libraries, and that's what we're trying to do right now. So the chemotype mapping tool that Carolyn mentioned, Chi-Hye has developed in conjunction with the FDA. This is about a year's effort of intellectual construction of a set of 660 chemical features that can be combined, actually, so you can get a factorial increase in the number of combinations of these chemotypes. But it's a candidate set that actually provides excellent coverage. I believe it's about 98% of our ToxCast chemicals have one or more of these chemotypes, and the majority of our chemicals have 5 or more of these chemotypes. So you can begin to organize your chemical space at an intermediate level instead of down here, in the same way that we're organizing our in vitro space. And what we are then trying to do is we're saying, okay, if I'm trying to go to from HTS assay data to predict in vivo outcomes, I'm bringing this prior knowledge. I'm trying to build pathways into my arguments. I'm trying to look at where the different gene targets might feed into a single pathway. Let me aggregate those results, everything to build up numbers. And now let me bring these features in. Let me map the intermediate chemistry to the intermediate biology and superimpose those. And can I use this now to help guide where I can go from the structure alone? So once I genericize the chemical to features, then I have the potential to bring in new chemicals and say, here's features that map these features that map onto the intermediate biology, and let me stepstone from these different data domains. And it's all about data integration, and it's all about really trying to marry this chemistry in a more intelligent way. So, and this is just an example that Chi-Hye has actually worked with data within FDA, merging it with EPA to build up a data set that was large enough that she could actually pull out different chemical subsets, and within those subsets, looking at the reflected in vitro results, could actually tease apart which of these chemotypes were really feeding into this endpoint. So I really believe that this is where the SAR community needs to go in terms of trying to deal with these new data. There we go. Okay. And I think one of the big problems, being the last speaker, I will just say, I think E.L. Wilson wrote a book called Consilience many years ago, and he said the biggest challenges in science are really at the interface of our disciplines, and I still believe that to be the case. As a chemist, I hear many biologists say, well, I don't know anything about I don't know anything about the chemistry, so I'm going to just let somebody else deal with it. The chemists are just as guilty of that. They don't know about the biology. The modelers are guilty of that. They just want ones and zeros. The statisticians just want numbers. It's really hard to get the two together. One way to do that is to incorporate the knowledge into these descriptors. The biologist bringing a modeler pathway-based data is going to help the modeler better model that endpoint. The chemist bringing the biologist chemotype level data is going to help the toxicologist interface with the chemistry, in my view. So we're hopscotching among these different data domains. I believe this is how we're going to really make some significant progress on this problem of toxicity prediction. And from the standpoint of within EPA, linking up to Matt's talk as well, I think QC curation, it's painful, painfully painful, but it's absolutely necessary. And you just do it once. You know, you do it once and you do it right, and then you build on that. You don't go back and have to do it again later on. Public data release, absolutely essential. Everything should be going out. All of our efforts are transparent. It may not be perfect, but you put everything out there, and then people can criticize. We can make it better. They can try to propose how to do it better. Come on. There we go. And I'm just going to press the last one, too. Using all of the available data. Don't tie one arm behind your back just because you don't understand that data. We've got to figure out ways to use all the data because the problem is just too big. the problems are too hard. We can't afford to throw away some of the data. And then finally, we have to deliver this data to the people who actually need to use it in a way that they understand. And I think all of these things are doable, and we take it a little piece at a time. And finally, just we have a small but very productive group, I think, and I think EPA is really at the forefront of trying to make some real progress in this area. And with that, I thank you.